Okay, good morning, everybody. I hope you guys are doing well. Um, Today is a good day. We're going to talk about some vitally important hypothesis testing questions. And, this is kind of what's going around you guys at this very moment. So it's a very good teaching moment, even though it's a very troubled thing, right? Um, So the troubling thing is we're talking about, you know, this virus out that's going out, this COVID-19, and people are testing various vaccines, various treatments, and you have to do this scientifically. Okay. So that's what's happening. And, we're going to get to see the exact mechanism for which this is happening. Meaning we're dealing with the scientific method with hypothesis testing, and we're going to be comparing two proportions here. So, let's lay some groundwork for you guys here on this. And before we do that, okay, we have a remark and quick message. I want to spread. If you are a grad that is going to be doing the virtual graduation this semester, don't forget to turn the required forms and pictures. Okay. Um, I believe Michael, the school. I mean, you guys should be paying attention to probably the school correspondence, and I mean every correspondence, and hopefully, I have heard that the school does send you guys emails and information. So hopefully, you guys are hooked into that, and that you aren't left out of any vital information that pertains to you. So make sure you guys are aware. Even the things that I send to you via announcement. You guys really want to be up to date with those things too, because it's vital for yourself. You're going to have your last test, you're going to have your final. So things like being able to scan your work, right, is going to be something you need to be functional with. How to upload your work and make sure your scans are clear. I mean, it's unbelievable what I have to deal with. Scan it the way it could be so people can read it and upload it, and make sure you keep track of your time. You don't have all day, or when you decide it's due, it comes in. It doesn't work that way. So remember, you guys, there's a lot of little things that are happening right now. And I know whether people like it or not, we all have to handle it and deal with it. Whether it's you, my own daughter, everybody. This is not something that is a situation that we chose, but we have to adapt. And when we adapt, we grow and we get more confident. We get better able to handle things that come our way. And so that's kind of the idea. So make sure, whether it's graduation information or your class information, make sure you guys are good to go with that. Keep up with it, because you might miss some important thing. And, it can impact, what happens with you. So, so hopefully you get whatever communication the school sends you. You get any communication I send you via announcements, and, you follow up on these ideas. Okay. I have resources for you guys again. I have the resources that are placed online. So if there's any issue for you to say, well, I don't understand one thing, double check that. Go over it, right? So anyway, and of course, you can see me during office hours, and I sent you guys an announcement to office hours where I merged classes together so that you guys can, it's not like, hey, you email me if you're not getting in. So everybody has the same window to come in through. So, double check that. I sent that in your announcements. I send it every week now. So it's in there. And so you can come see me, and people have. So just make sure you guys are good to go with what you need to be, with. Okay. And anyway, let's get to the good, juicy stuff, the stuff that really pertains to your life, like hypothesis testing and the concept of, comparing two proportions. So let me start to write some things down so that you guys, can understand the concept here, right? So remember, we're going to start with two independent populations here. And here's our rectangle, I guess. So we have population 1 and we have population 2. And they need to be independent. I mean, the data is independent here of one another. Data I actually prefer the phrase in this case, mutually exclusive. Okay, because mutually exclusive means that data values that are in each population. So these dots represent random data values. Data values in population 1, and then you have data values in population 2. Mutually exclusive means a data value can't belong to both. Okay, so we're going to take some data here from each population, and it can't belong to both sets, really. Because remember, this is hypothesis testing. And with hypothesis testing, yes, you're going to end up taking a sample here. And we're going to have 2 samples. Sample 1 and sample 2. And we're saying you can't have a data value that's in both populations or both samples. They're independent of one another. They're mutually exclusive is the better phrase. Now, give you some examples. We can compare 2 different groups. Population 1 can be men. Population 2 can be women. So you can't belong to both. You can't be both a man and a woman at the same time. Okay, you're either a man or a woman, but you're not both. So these are 2 mutually exclusive, or what we also say is independent populations. You could be, for example, a boy or a girl. You can be either. But notice you can't be both. You can't be a boy and a girl at the same time. So we can compare populations, boys, girls. We can even say, go back to the idea of men, or I should say, I can say men here versus boy. So we can compare those 2. Now, you say, what's the difference between a man and a boy? Well, for a man, you're a male at least 18. For a boy, you're a male that's under 18. So this kind of language, ladies and gentlemen, is important. That's why I use at least, less than, because it's used. So we can define, even males 2 ways. Men, boys. Same thing for women and girls. So we can say, you could be a woman. You could be a girl. 2 different populations. A woman is a female at least 18. A girl is a female under 18. Okay, so we could define it that way so that they're independent or mutually exclusive. That's the idea, right? Can't belong to both. You could be, let's say, for example, there's a treatment. We have a certain president that thinks maybe, I don't know, Windex. And I'm not sure if you spell Windex that way. Let's double check. You might think Windex is a good treatment for, who knows? I don't know. Windex. Maybe just say for a rash. Okay. Yeah, we spell Windex okay. All right. Windex is spelled that way. So maybe you say, I have a treatment. One group is going to get Windex, and the other one is going to get some other kind of lotion for a skin rash. So we're going to compare 2 groups to see, which treatment maybe works. The Windex treatment are the people that apply some special lotion. Okay? You could even say, guess what? There's some special vaccine. Okay? And they're looking at trying to develop some vaccines, I guess. And they have to tell, well, is this vaccine going to work? Okay? Well, you can get a special vaccine And then you compare that to people who get a placebo. Now you say, what's a placebo? A placebo is actually, a fake medication. They're trying to blind you. See, they want to know, or they want to make sure you don't psychologically somehow cure yourself if you have knowledge of whether you're taking the vaccine or the placebo type of thing. They're trying to blind you to that reality. So what they do is they tell you it's a vaccine in both cases. So one group gets the vaccine, the other one gets the placebo, but they're told they're both getting the vaccine. And what happens now is they truly measure. And a placebo is also known as the sugar pill. They commonly call that, somebody got a sugar pill instead. And so they want to see which group actually gets better. Okay? And at what rate. And so these are the trials that are happening at this very moment. Okay? So I'm just looking online here really quickly. I don't know. Let's go to the website to show you some more information about how this works. So go to the browser, right? And the browser, vaccine experts say Moderna didn't produce data critical to assessing COVID-19 vaccine. Okay, I don't know the details. I haven't even read this article. But this is kind of the idea exactly of what we're working with at this time is, they go through a process and a procedure to test to see whether this vaccine works. So, yeah, let's see if this even makes sense. Anyway, N equals 8. Okay. Yeah, they check the doses even. They test these things. So these are some of the little details they do go through. And I'm just kind of looking at this. I just randomly looked it up and showed you guys that this is the kind of information and the kind of process that you're studying right now directly with hypothesis testing, and it affects your life. Okay? So this is what's happening. So it's a very good day or a very good time to study statistics, ladies and gentlemen, and probability, because it applies to us in a very big way. And we're going to compare now. The title of this is Hypothesis Testing Comparing to Proportions. And a proportion, if you guys remember, is P. P stands for what? Not population. P stands for a proportion. And a proportion, right, is a percent or probability. And the definition of a proportion, this is P. This isn't P hat. This is a population proportion. That's what P represents. Population proportion. The definition of a population proportion is X over big N, if you guys remember. That's the number of successes divided by the total in the population. And that's the true value. Now, the second you take a sample, you're approximating. That's P hat. That's sample proportion. And so what I'm going to indicate now is that you have this P1, that's the proportion, right? That's the true proportion from population 1. That's what the 1 stands for. And down here you have a 2. P2. That's your second population. That's your population proportion for the second population. That's the true value. Now, if you take samples, of course, you have the sample proportion from group 1 and sample proportion from group 2. So this is the symbolism. And remember, a sample proportion based on a sample is X over little lowercase n, little n, right? It's the number of successes divided by the sample size. And that's your definitions here. And so here's kind of what's going on here with this situation, and we're going to compare. Now, remember what we did in the past. We were working with hypothesis testing with proportions in the past, and we had 3 kinds of decision rules. Well, nothing's changed, meaning here's what's going to happen with your decision rules. Situation 1, you have P1 equals P2. P1 does not equal to P2. So here's our first kind of test. Of course, you guys remember everything is the same. So I'm going to go through a sketch of this idea so we can look at this, and it's based on what you've already done. And let's kind of draw a straight line. There we go. These are going to be large samples, so it's going to be a Z distribution. Now remember, you always know, and that's always, that this is a two-tailed test. And you say, how do I know it's 2 tails? Right here. When it's not equal, you always have 2 tails. So we have a left tail and we have a right tail. We still have do not reject the null region. And over here, we have reject the null. We have reject the null. And you're going to have a critical value and a critical value because this is a 2-tailed test. So this is my first type of hypothesis setup at my decision rule. So you're comparing populations here that for the null, there's your condition of equality. For the alternate, it's not equal. So there's our first decision rule. The only thing that you guys have that's new, to tell you the truth, is in the past, you had this value compared to a number. Well, it's now compared to another proportion. And this is the new part in red. Okay, so that's what's new. And then you'll see the language associated with comparing to proportions, because this is language based. Okay, let's look at the second type of decision rule. So the second type of decision rule that you guys are going to have here, here's type 1, type 2. We're going to set it up the same way. We're going to say, okay, H naught and H1. P greater than or equal to, and that's P1 greater than or equal to P2. And the opposite of that statement is P1 less than P2. Okay? So here's my second decision rule, and it's just like before. Again, just like before, you always look at the alternate hypothesis, and right in there you have pointing to the left. That's less than. So your decision rule in this case is going to be a left tail test. We're going to deal with large samples. The Z value. Now, remember, this is pointing to the left, so we have a left tail test. So you have do not reject the null. And over here, you have reject the null. And you have a critical value. This is a left tail test, right? So this tells us what to do. It's left tail. Okay, that's the second type of decision rule, and nothing's changed. It's just like before. The only thing that's new is the comparison of two proportions, percents, probabilities, likelihood. That's the only thing that's new, comparing these two. So, all right, there we go. And here's situation number 3. H naught, H1. So we're going to have P here less than P1, less than or equal to P2. And the opposite of that is P1 greater than P2. And you're going to look here at this alternate hypothesis. Zero. We're going to deal with large samples. That's a Z distribution. Again, it's a right tail test because that inequality is pointing to the right. So if it's pointing to the right, it's a right tail. My decision rule is exactly like before, right? We do not reject the null. And here, you reject the null. So there you guys go. You do need, again, a critical value. So ladies and gentlemen, notice the only thing that's new, the only thing so far is that we're comparing, you're comparing here two proportions, one from each population. Okay, from each population. And we're really comparing two groups. I mean, there's a lot of ways we can look at some of these questions, but, you know, I think in honor of what's going on, it's probably very, very good to be very sobering with some of these things so that people can really understand, wow, this stuff is used, it is around you. This is why you study it. You know, education is something that's supposed to empower you, right? So this is the idea, empower you to understand the world around you. And this is your 3 decision rules. So a couple of things are going to happen here now. I think, you know, we can look at an example, and when I look at your book, you know, let's see if they have, yeah. When I look at your book, question 5 in your book is a very good question. I kind of like that right off the bat. And, you know, this is about gloves, comparing effectiveness of 2 types of gloves. So this is titled testing laboratory gloves. And you might say, what are you talking about? Well, they're talking about 2 types of gloves. One type is vinyl. So I'll write this down. Vinyl really versus latex. And they're testing the effectiveness in regards to leaks. Okay. So, I mean, I recommend, you know, for students with this text, I recommend you guys always read these examples and go through them because they're very good. This is one of my favorite math books, even though it's gotten, you know, they've watered it down through the years. It's one of my favorite because of the fact that you get to read questions that are real life. And, you know, this is a real life kind of test. In fact, it came from a New York Times published article, and it's saying the article was a study about, you know, Professor Denise Kornwitz and other Johns Hopkins researchers subjected laboratory gloves to stress. They want to test for leaks. And so here's what they're saying. From the study, here's what they found. Among 240 vinyl gloves, 63% leaked viruses. Wow. So among the study, 240 vinyl gloves, 63% leaked viruses. Okay. And I'm going to change this a bit. I'm going to change it. Among 200 latex gloves, 7% leaked viruses. We're going to say use the 1% level of significance to test the claim that vinyl gloves have a greater chance of leaking viruses vinyl gloves have a greater chance of leaking than latex gloves. Latex. Okay, so here is your very, very first kind of real life hypothesis testing question where we're comparing two populations. Now, you're saying, well, what do you mean? How do I know it's a hypothesis test? Because they're going to say to you, what are they going to say? Test the claim. And then you're going to say, well, what's the claim here? I don't know. What's the claim? Well, you're going to have to read it, and then we're going to have to really look at the details of this, right? That the vinyl gloves have what's the group? Vinyl gloves, and maybe we should put that in red. We don't have to. Vinyl gloves have a greater chance of leaking viruses than latex gloves. And so there's probably some things we have to really note. I like to keep things simple. When they say greater chance, I know this inequality means bigger. And then you might say, Mr. Judge, what do they mean by chance? Anybody have an idea? Let's ask you guys. What do you think when they have the phrase here, chance? What does that actually mean? Anybody know? What's the parameter for chance? Anybody know? What's the parameter for chance? Has anybody ever thought of, what did we say? I think I gave you the definition of this. It's called the measure of chance. Yes. Thank you, Catherine. It's probability. P. Okay? There you guys go. See? I'm telling you guys, this can be done. Okay? It's a probability value. It's P. Okay. Good. All right. Now, when I say to you, what's the claim here? Because we want to write down this claim. Here's what you guys want to consider. Vinyl. P vinyl versus P latex. Because I read this phrase first. P vinyl, and this is greater than latex. You read left to right. So, ladies and gentlemen, this is the hypothesis that the probability of the vinyl glove leaking viruses is greater, larger than the probability of the latex gloves leaking viruses. And this, here's what I'm going to say. Write this as a claim. Now, there are people who, and you know, if it's okay for now if you say to me, you know, Mr. Judge, I understand the process. I just don't know my conclusion, because I'm getting messages about that. So I want to use this as a teaching moment again for people, since that's what I do, right? So those of you that are contact me going, hey, wait a minute, I don't know, how do I draw my conclusion, right? Well, this is where it starts. You have to know what the claim is, because after all, this is what we test. We're ultimately testing the claim. Okay? We're testing this. Well, what's the claim? What did they say the claim was? They said, this is the claim. So that's what we're really testing. All right? Don't even think of anything else. If I'm going to give you that advice, don't try to make this more complicated than it is. This is the statement you're testing. So when you write this down, H0, H1, right? You have to determine, where does this claim belong? What type of claim is this? Is this a null or is this an alternate? And because there's no condition of what I say to you, equality, right? This is going to be an alternate. And I'm going to put V for vinyl and then L for latex, okay? I'm just going to write it down this way, and I read left to right, okay? If you start reading backwards, it's going to be a problem. So we got probability of a vinyl is greater than probability of latex. And that probability is measuring leakage of viruses. Well, that's not good. Okay, now the logical opposite. Now remember, when I write this down, I also put here claim. Claim. That's where your claim goes. So then you have PV versus PL, less than or equal. This has to be the opposite. Okay, so this is the null hypothesis, this is the alternate, and this is your setup. Anybody have any questions on the setup, how you set that up? Because we're going to have to go through the details of this. Okay, you guys okay with that setup? All right, now, let's ask you guys again. You should know this. If you've been working with this stuff, and I suggest you do, where do you put your eyeball? It is always the alternate hypothesis. Now, you say, why do I do that? I have to figure out what kind of test I have. And if my inequality here is, let's say that's pointing to the right. Remember we went through this? That means this is a right tail. The inequality is pointing to the right. This is my decision rule. I'm looking at it. And so you go, okay. So decision rule. It's right tail. This is the do not reject the null region. And this is the reject the null region. So ladies and gentlemen, you're going to have to write down your regions this way. Okay. There's a lot more math under the hood here. In fact, I would say if you really wanted to know all the gory details behind some of this stuff, you'd have to probably take at least you have to take the calculus sequence 1, 2, and 3. Then you probably have to take a probability course. That's another course. Before that, you have to take probably have to take advanced probability, maybe 1 and 2. So it's 1, 2, 3, 4, 5. There's about 6 or 7. It's really 7 math courses starting with calculus before you get into proving all the gory detail here. And so if you said, 7 math courses, yep. And that's assuming you start with calculus, right? Large sample. So what I'm saying to you is a lot of times there is going to be some of these details that here regarding to these procedures that are proven, and you can't go through every detail of it because it's about 7 courses. So what you guys are really looking at is how to use this stuff. So what I'm saying is you can't change your decision rule to be random. You have to write it as do not reject the null and reject the null. Okay, this is a lot more details. So here's your critical value. Now go back here. Go back and remember, what are they asking? Use the 1% level of significance. So alpha are 1%. That means if we say alpha is 1%, that means all of this area is 1%. But that implies that this portion here is 49%. Now you need to know this because you need to find the critical value. And the critical value, since we're dealing with large samples, is that Z distribution. So we're going to have to find the critical value with the Z distribution. Oops, apologize. Here's word. And you say, sorry, not today, T-table. Right? And here we go. We've got to go to the Z table now. Let's just clean it up since we're here. %. So where's 49%? Remember, you're trying to get as close as you can. And I see a candidate. Here's what I see. 49.01. That's 1 penny over 49. Now that's in row 2.3. And that's in column 0.03. So it's 2.303. Let's go back. Okay, that's where 49% is. So my Z value, and it's not 49, it's 49%. It's 1 penny over. So we've seen this before over and over again, right, with estimation and hypothesis testing. So the critical value is 2.33. So what we've been doing, though, is to say to you, if you guys remember, that any value less than any test statistic value, less than that critical value of 2.33, you're going to conclude that you do not reject the null. And then you say, well, what if the critical value is larger, right? I'm sorry, the test statistic is larger than 2.33. Then you conclude that you reject the null. And that's really not your answer, but this is where you start to get your answer. This is why they call it the decision rule. It helps you make your decision. So this is where this all compares. You compare the test statistic, and that's what we're going to have to write down. You're going to see where the test statistic lies in your decision rule, and that's it. And if you guys remember, the test statistic is just a formula. But I have a new formula for you. Since you're comparing two independent samples, really mutually exclusive samples. Oh, that's not straight. We have a different formula. It's not the same. So don't try to use the same formula for everything, right? You're kind of really missing the point, and then you can't even apply it because the sample information that you take and get by essence is different when you compare means and when you compare these proportions. So, you can't even use the same formulas. So understand that with your test statistics, you have different formulas, and you need to write those down. That's your job, right? This is when you study, you write that down for the formulas that you use there. So let me give this to you. It's going to be, we're going to start with P1, sample proportion 1 minus sample proportion 2. All right, you guys okay with that? That's in my numerator. Okay. Just looking at the notation in your book. Just want to make sure the notation is okay here. Yeah, I'm going to check this formula sheet online here. I'm going to check my browser. We're going to go to the browser. Let me double check here so you guys, so I want to be clear with this 227. Where are we at? Come here. So you go, here we go. Formula card. I want to show you here. So really where we're at here in the formula card, yeah, that's what I'm noticing. Okay. If you look down here, let me see if I can make this bigger. Yeah. It's right. Okay, right there. All right. So you guys see that it says two proportions there, right? So the notation is a bit different. And I want to warn you. Here's what happens with this. You see that P with a caret, that's really the sample proportion. And this portion over here, P1 minus P2, is really going to be 0. The bottom, you have the P and Q hat, and I'm going to say, no, that's not sample. I know, that's kind of a not good notation here. Okay? So in the book, you have an issue. So let's write down the formula here. I'm going to write down the formula that I've given and used here. I'm going to say P squiggle times 1 minus P squiggle. Let's make that big and clear. Over N1 plus P squiggle. 1 minus P squiggle over N2. And so you guys know already where you get the numerator from, but you don't know about this thing called P squiggle, and I'm going to give you the definition. This P squiggle is called the pooled proportion. And here's what they mean. You add the total successes and you divide by the total for the sample size. It's called a pooled proportion. This Q, which the book really gives you, is the complement of that. So we're going to have to go through these details here. It's not too hard, but when you first see this, yes, ladies and gentlemen, you're going to have to write these things down. These are what we use here for this, and this is what's in my video. So make sure you guys have this down now. And here's the deal, okay? Here's what's going to happen. This is all based on a sample. But remember, you have two samples, sample 1 and sample 2. So you really have to be careful here. Here's what I mean where you be careful. If there's two samples, what's sample 1, what's sample 2? But before that, what's population 1, what's population 2? Go back to the hypotheses and you read left to right. This is really P1 and this is P2. Isn't that what you have from your decision rule, right? In general, P1 versus P2. But keep track of your groups. The first group is the vinyl. The second group is the latex. That's an important detail because I need to now take the information for vinyl. Sample 1 is going to be for the vinyl data, and sample 2 is the latex data. You have to have these groups correct. Otherwise, your answers are going to be opposite in sign. Okay, Sandra has a good question. Will the eyeball always be placed on H1? The answer to that question, Sandra, is yes. H1 is always going to be what you look at to determine the decision rule. And it says, regardless of where the claim falls, yes. It doesn't matter. It's independent. Your claim, and this is where some people get confused, they want the claim always to be a null. Or they want the claim always to be an alternate, because the last example was that. You're missing a very important detail. People don't think in terms of null hypothesis. They don't think in terms of alternate. A claim is independent of that. So a null can be, a hypothesis can be a null or an alternate. Don't force it to be what you want it to be, right? So you accept the hypothesis and where it belongs. That's the claim. But if you want to see the decision rule, you always look at the alternate hypothesis. So don't try to come up with a shortcut, meaning here's what you look at. And really, you're looking at this. So the claim could be a null. It could be an alternate. That has nothing to do with, the decision rule, only in the sense. It's not linked to the claim. Your decision rule is independent of the claim. It is always looking at the alternate hypothesis and that inequality symbol. If the claim is a null, then the claim's a null. If it's an alternate, it's an alternate. So it's independent. It doesn't matter. It's not the point, is what I'm saying. Just look at the alternate. That tells you your decision rule. But I really want to say what is important is you keep these groups what they should be. Sample 1 is vinyl. Sample 2 is latex. You say, why? Because we wrote it that way. Population 1, population 2, reading it left to right. So there you guys go. And then you say, well, how do I get my sample information? They're giving it to you. So we need vinyl first. You say, what do we mean? What do you mean, vinyl? Well, what do they say? 240 vinyl gloves have 63% that leaked viruses. So N is 240. Now you have to know, what did they give you? 63%, ladies and gentlemen, is from a study, from a sample. That's a sample proportion. So I'm going to write that down, 240 and 63%. So N here is 240, and that first, that's P1, is 0.63. 0.3 because we always use the decimal representation of 63%. So that's for the vinyl group. And then you read the rest, and it says, what do you mean? 200 latex gloves had a 7% leakage rate. So this is a sample from the latex sample, and this is the sample proportion, it's percent, of 7%. But the decimal representation is 0.07. So for this group, and here is 200, and then over here, .07 is 7%. All right. So ladies and gentlemen, here's where we're at. So if you said to me, well, what do I plug in for my test statistic? Well, for group 1, this is 0.63. For group 2, it's 0.07. So we're plugging these values in. Okay, so this is what we just found. We found this, we found that. Make sure it goes in the right place. That's why I say keep track of group 1, keep track of group 2. Now, we know the sample size for group 1, they told us was 240. We know the sample size for group 2, they told us was 200. There you guys go. You need the pooled proportion and the complement. That's the same value here and here. So we need the pooled proportion. Now, pooling, like if someone says, here's that P squiggle, a pooled proportion. If someone says you're pooling your resources, pooling, not pulling, pool, P-O-O-L. To pool your resources means to put together. Put together. So you have X1 plus X2 over N1 plus N2. Now, you might say, but they didn't give me X1 and X2. They gave me N1 and N2. They gave me this 240, and they gave me this 200. Ladies and gentlemen, samples don't have to be equal for each group. They could be different. But you say, well, how do I get this? Well, here's what you're going to have to do, right? The definition is X1 over N1. I can solve for X. X1 is that pool proportion rate times the sample size. Now, similarly, for the second one, X2 over N2. And so that means X2 will be the second times N2. So the number of successes in this case is 0.63 times 240, and X2 will be 0.07 times 200. So you need this X value, X1, we need the X2 value, and that's going to be used to get our pooled proportion here. Okay, so they gave it to us this way. Now, ironically, if they gave us the successes, and we'll see that, they're going to give us successes. They just want to give this as a first example. We need to find these values, and that's where the calculator comes in. Okay, TI-84. Here we go. 0.63 times 240 is going to give you about 151. So round off to the nearest whole number, 151. The next one is 7% of 200. 7 times 200. And that's 14. So X2 is going to be 14. So when we compute the pooled proportion, you say, do I put 151 here plus 14? I do. Now let's see what we get for a pooled proportion. So I'm going to erase this here. So we need that pooled proportion. So The pooled proportion is going to be found by taking the sum. $151 plus 14, 240 plus 200. Here we go. We're going to add these values, right? We're going to go to the TI-84. So we say 151 plus that 14, and probably, let's be very smart. Put it in parentheses. 151 plus 14, close that, divided by, now add your sample sizes. You're pooling your resources, 240 plus 200. Close that. What do we get? 0.375. So, ladies and gentlemen, this is actually 37.5%. Okay, 37.5%. So, if you said to me, where do I put that? That goes right in here. This goes here. This is your p hat. So 0.375. I'm going to erase this so you can see it. But notice this portion now. We need the complement of 37.5%. So going to the TI, we have 1 minus 0.375. And we get 62.5%. 62.5%. So this becomes 0.625. And you just repeat this, 0.375 and 0.625. So what's new is this pooled proportion. The symbol I use is that squiggle. And this is the definition. And that's what's new. So if I erase some of this stuff and I'll say, like I've always said to you guys, I really write it down again. Test statistic. 0.63 minus 0.07 over 0.375 times 0.625. First sample size is 240. 375 times 0.625. Sample size is 200. This is what you guys enter in your calculator. Okay? And another thing, remember how you enter in your calculator. This is one thing to show people, is that you're going to put a parentheses around the difference in the numerator. And then you're going to show, I'm going to do this. I'm going to show you guys, you have to do a double parentheses here. Because you have to tell the calculator, hey, calculator, I have this arithmetic to do separate from, and I'll color this arithmetic to do. They're separate. And this is why we separated them with some parentheses here. And the arithmetic here in the numerator, I'll just color green. So this is why we put the parentheses around the arithmetic. And don't forget, we have this in the middle here. This is addition. So sometimes people mistake the signs, right? They don't put the right signs in, and they'll make an error. They'll have an error because the sign is incorrect. They'll put times or minus, and it's really plus. So I'm going to show you guys, take a good look at this. I'm going to double check to see if this is exactly what we have here. It looks like it is. Let's find out what this is. We got to go to the TI. So here we go. We say, okay, TI, let's enter everything. So remember, the numerator has a parentheses, 0.63 minus 0.07. You're going to close that. Now, you're going to divide. You say divide by what? There's a double check. You're going to divide by a square root, right? There's a square root here. So divide by a square root. So I got to find, okay, that's second square root. There we go. Now, open a parentheses, because what I'm about to communicate to the calculator is that everything that comes after this first set of parentheses is what's under the radical. And that's what I have to tell it. I have to tell the calculator there's a lot under here. That's why you put that first set. And then, like I said here, if you go back and take a look at the iPad, there's a double. So this is the first set right here. And then I have another parentheses. I'm going to put some arithmetic and close it. So that's what I have to communicate. So open another parentheses, 0.375 times 0.625 divided by the first sample size, 240. Close that parentheses, ladies and gentlemen. And this is where we're at now if I go to the iPad. Now I have to tell the calculator, hey, calculator, add. And you say, add what? You're going to add another computation. So I'm going to have to add and put another set of parentheses. All right. Okay. Plus another set. 0.375 times 0.625 divided by 200. And then you close that parentheses. That's the second set of computation there. So we now have to finish this off by putting the last parentheses. Because if I don't, I'll get an error. And the rest of your calculators work this way too. So I'm going to say put another parentheses, and remember, with the TI, you have to get out from that under that radical. So you're out from under the radical. And so now, ladies and gentlemen, guess what we get to do? You get to hit this thing called enter. And you say, what do I approximate to? You always approximate to your place value in your decision rule. So the place value in the decision rule, really the critical value, you approximate to that. It's in the nearest 100th. Okay. So here's that test statistic. 12.08. Michael, if your calculator put the parentheses after the square root, you're lucky. That means you don't have to put that first parentheses. You do everything else the same, though. It just means for you, the calculator automatically put a square root for you. You're a lucky guy. Good calculator, right? So if your test statistic is 12.08, what does this mean? Now, this is what you guys have to focus on, because people are going to say things like, oh, I understand how to do everything, but I don't know what it means. All right. You got a problem here, because you can't go about testing hypotheses if you don't know what the conclusions mean. You know, it's kind of crazy. It's like saying for the scientific method, oh, scientific method, I don't know what the conclusion is. Then you don't go through the, it's very problematic. So the test statistic is 12.08, right? So let's go back, and it's this simple. It's very simple, but the problem is people make a lot of assumptions. 12.08 in comparison to my critical value of 2.33 is probably way over here, right? 12.08, I guess that's the value. It's really way over here. So I'm going to go, okay, if I extend all this. So since the critical value is beyond that, or I should say the test statistic here is beyond your critical value, that 12.08, what region is that in? It's in the reject the null region. And so I'm going to write this down. It's not my conclusion exactly, reject the null. Now, here's what happens. It says to reject your null. So, what do? You do what it tells you to. You reject the null. The null is rejected. Let's say that again. The null is rejected. The null is rejected. Let's go to the null. Say, here you are, null. Here is the null. Guess what? You are rejected. We just rejected the null. Okay? Now, let's ask you guys this question. When you reject the null, what's your conclusion in relation to the claim now? And let's see. We got Sandra. We got Catherine. Who's correct? One person says a sample supports the claim. The other person says the sample does not support the claim. Let me give you guys a little hint here, right? Why do I even write down the claim next to it? Okay, because why do I even write down the claim? Is that important? I'm testing it. The decision rule is to throw out, to reject the null hypothesis. When you're rejecting the null, it's gone. What is left? The alternate is left. The alternate happens to be your claim. So the person that's correct in this situation is going to be Catherine. The sample supports. Oh, sorry. Let's go back. Person that's correct. Who's correct? Sandra. The sample supports the claim. Who else is correct? Joanna's correct. Who else is correct? Leopoldo's correct. The sample supports the claim, ladies and gentlemen. And there you guys go. That's the deal. The sample is supporting the claim. You go, why is that? You threw out the null hypothesis. You didn't throw out the claim. You're accepting the claim. So here's our formal conclusion, right? And this is what happens on a test. What I'm looking for is this answer. The sample supports the claim. There's only one conclusion, ladies and gentlemen, that the sample supports the claim. Okay? Only one. And anything else is going to be wrong, because this is the formal test. This is the basis of saving all our lives. You're not free to write anything random and inconsistent, right? So what you would say in a legal document here for this particular test of gloves for virus leakages, that the sample information is suggesting that, that the proportion of virus leakage for vinyl gloves is in fact greater than the proportion for latex. Okay, now let's really think. Which glove would you use? Oh, that's $1 million question for you guys. What does this all mean in the context of COVID-19 even, and, gloves, vinyl versus latex? What is this? This is an additional question that's kind of common sense, but it tests whether you know about the definition of probability and what that means. Which glove would you buy at the store with this test? With knowledge of this test, Are you going to buy the vinyl glove? Or are you going to buy the latex glove? Which one are you guys buying? Okay. Sandra says latex. Guess what, Sandra? You're right. Get the latex glove because the chance of leakage is actually smaller than the chance of leakage for vinyl. This is the meaning of reading about these probabilities, right? There's a less chance right up in here. And I know we have all these colors in the way, but there's a less chance of leakage when you do the vinyl. That's the meaning here, ladies and gentlemen, of what this test was about. All right, they're testing that claim, and what we found is that the evidence suggests, and that's another way people say this, that by the way, that the evidence suggests that the chance of leakage is smaller when it's actually latex. You don't want virus leaking, right? You guys know what I'm saying? Under your hands from the gloves? You don't want that. So there's a less chance. You go, how do I know? Well, take a look at the sample. What did the sample say for latex? That's 7% versus 63% just for the sample information. That's measuring leakage. So the smaller percentage in this case is the beneficial product. Okay, you want even less leakage if you can get that. 63% is a pretty high leakage if you use vinyl. So don't use vinyl gloves. You use latex gloves. And that's why you see, ladies and gentlemen, if you go into the medical field, why they're using latex gloves when they handle a lot of things. Because they have a less chance, smaller chance of leaking the virus onto them via their hands. Because that's where they put the gloves. So this was a very, very, very good lesson today on what we'll be working with in our future, which is, we're going to be comparing two proportions here with things that are relevant to you in your life. And I wanted to go through, the decision rules today, and I wanted to go through the test statistic right here, which we did, and I wanted to go through even the definition of pooled proportion. And that's kind of what's new for you guys. So, anyway, it's a good day. It's a very, very good day. So, ladies and gentlemen, here's what I'm going through now. Looking at your book. Anyway, try this out. And Sandra, you're correct. I would say to you, what you're going to continue now for homework, though. I'm not going to give you homework from the book today. Go to the browser. Here we are, browser. Right, so we looked at this test statistic today, the true proportions, right here. I just wanted to clarify notation that I use, and I deviated from the notation from the book because, I really would criticize whoever wrote that for writing what they did. I understand why they did it, but anyway, they just changed the symbol for a sample proportion for you guys here. For those, and they kept it for the pooled proportion. That's all they did. I just disagree with it. But nevertheless, if we go to the browser and we say, here's statistic library, right? Let's go there. Yeah, internet seems to be pretty slow today. Jesus, don't pay for 1 gig. I'm glad I paid for the gig. What would it be if I didn't? So we're looking at this. We were looking at it yesterday. What you guys seen here is the start of questions like 15 and on, 15 to 20, and then we have 21 to 21 and 22. So really what I started today, based on your book, were these questions here, and we're going to do some more tomorrow. Oh, no, sorry. We started today were these questions here. Sorry, the book it's correct. And as you guys can see, there's two different samples, and so you guys can get started with 15, 16, 17, 18, 19, 20. We're going to do some more because, it's a very good teaching moment for what's affecting all of us at the moment. And we're really looking at these, and I want to go over some more. Maybe we can do at least one more. It doesn't matter, or two, who knows. But we're heading into this kind of area, comparing two population parameters. And then we can compare two means, and that's what we're going to do after we compare two proportions and compare two means. So you can start on 15 through 20 now, these questions for tonight on statistics lecture, what is it, 14, and hypothesis testing. And then if you said to me, boy, Mr. Judge, I really want to watch another lecture. I don't understand much of what you just went through. Well, guess what? I have, for all of hypothesis testing in 720p, right? I go through these details. So, you have information. See, this is comparing two means already. I can see that. Yeah, comparing two means. And we're starting to compare two proportions, I guess, here. So there you go, a pooled proportion. There it is. See that piece squiggle? You guys can't see that. Let me see. There it is, Statistics Lecture 14. So continue those questions. If you have any issues, concerns, you guys can always see me in office hours. I sent that announcement via Canvas, and there you guys go. So stay safe, work on these ideas. We're going to continue with this tomorrow. I just wanted to go through every detail that you can see and talk over, again, the conclusion. Hopefully you guys emphasize that. So anyway, stay safe, work on what you need to work on. And if you have any questions and issues, see me in office hours, and I'll see you guys later. Okay? Take it easy.